Alright guys, there are 4 practice problems. I'm going to do 2 in this video and we'll see how long it takes. So a stone is dropped down a well that is 400 feet deep, and first we want to know how long it's going to take to reach the bottom. So I want to figure out the time when its height is either negative 400 or 0, depending on how I draw this picture. So I'm going to draw the picture of the well, and the ground is here, and there's the well. I would draw a picture. So if the ground then has a position of 0, then this down here is going to be negative 400. So 0 feet at that time. Okay, so you could draw it like that. You also could draw it where the top is plus 400 and you're trying to get to 0, but you're going to see that it's not going to matter. So what we want to know is how long that's going to take. And right now I don't even have a position function. So I need a function that models the position of any object on Earth in free fall, because the stone is just in free fall. So we always kind of start with the fact that acceleration is a constant negative 32 feet per second squared. Okay, but it's the negative 32 that we're going to use here. Those would be the units. But so our acceleration function, which you'll recall is the derivative of the velocity function, is negative 32. Now, to find the velocity function, we have to take the antiderivative of negative 32. So that's going to be negative 32 t plus some constant, right? And I'm going to put 1 there for our constant because we may have another when we go to our position function. But here's what we know right now. We know that the stone is dropped into this well. So initially, when the person, and I'm assuming that this is a person here, like leaning into the well, about to drop the stone, initially, before the stone is dropped, right initially, it has no velocity at all. So that matters, right? Because that's an initial condition that tells us that the initial velocity, since it's a stone that's being dropped, is 0. So now I can use this formula here. V of 0 equals negative 32 times 0 plus C1 is 0. And so that must mean that there is no constant here. So I can eliminate that, and I can say that my velocity function is just negative 32 times the time. Okay, now let's use that to find our position function, because remember, velocity is the derivative of position. So our position function would be negative 32, sorry, not negative 32. It's going to be t squared, and I have to figure out what I can put as a coefficient to that t squared that would give me negative 32. So that'll be negative 16t plus c. There is a constant here, and this is where we actually have information that'll allow us to find this constant. Another thing that I know, and it goes back to our original picture, is that initially, when we're laying about to drop the stone, the height is 0, the position is 0. So we can say again that to find this constant, s of 0, which would be negative 16 times 0 squared plus c, that's also 0. So c2, if we want to look at it like that, is also 0. So my position function then is just negative 16t squared. So now that I have that position function that goes to this picture and lines up with the way we've drawn it, we can find the things we need to find. I want to know the time when it reaches the bottom. So I'm solving for t, but I want to know what t is when the position is at the bottom. And when the position is at the bottom, it's going to be at a height of negative 400. So when is s of t negative 400? Or in other words, negative 16t squared equals negative 400, and I have to solve this thing for t. All right, so this is a quadratic. I should probably set this thing equal to 0 first. And now I have to find a way to solve this formula here, solve this equation. So you've got some choices. what you could do to actually solve this. But what I'm going to do is factor out a negative 16. So that's going to leave me with t squared minus 25 equals 0. And so then my solutions are going to have to be, or my factors will be t plus 5 and t minus 5. And I don't necessarily need to account for that negative 16 at this point because I'm trying to figure out what's going to make this thing 0. So that would be at plus or minus 5. And so whichever of those makes sense, right? Does it make sense that in negative 5 seconds it will reach the bottom? Or does it make sense that in 5 seconds it will reach the bottom? So therefore it takes 5 seconds. All right, the second part of this question is, what is the velocity when it strikes the ground? So this is why we needed to go through all this effort of finding these equations, because now I want to know what velocity it's moving at when it hits that point. And another thing I know is that when it hits that point, it's at the 5th second. So what I can do is use my velocity function that I came up with, this velocity function, and just figure out how fast this object is moving in 5 seconds. And I'm only able to do that so easily because I already figured out how long it takes to get to the bottom of the well. All right, so this is our solution to A. Let me just try to keep my work organized here. And then so for B, all I want to do is find out the velocity after 5 seconds. And our velocity function is negative 32 times t. So at 5 seconds, negative 160 feet per second. And the reason that that can be negative is because we're indicating direction, right? So we know that the rock is traveling downward, and that's what that negative is indicating. So you can say negative 160 feet per second because it's indicating the direction. We would not say that for time because we can't go back in time, right? That doesn't make logical sense, but we can have a negative velocity. Let's do one more of these. So an arrow is shot straight up in the air, and this is sort of the reverse of the previous problem. You've got a guy here, and actually we should make him laying down because of the way that this is worded. So again, he's laying down on the ground, and he's got a bow and arrow in his hand. Not great, but he's about to shoot this arrow straight up in the air. And it's shot up with a velocity of 128 feet per second, which tells us something, because now we know that initially when this arrow is launched, it's going 128 feet per second. So we've got an initial condition. The question is, how high does it go? Okay, so again, we can start by just saying we know that acceleration is negative 32 feet per second squared. And so that means that velocity is going to be negative 32t plus c. But this time our initial condition is a little bit different. This time I know that v of 0 is negative 32 times 0 plus c, and that is 128. So c is 128 now. All right. So I can say that v of t is more specifically negative 32t plus 128. So now I could answer this first question because one thing that I know about its peak, the highest point that it reaches, is that this arrow is going to be really quick initially, and then it's going to slow down, and then it's going to stop and come back down. And when it stops, it's at its peak. So what I can say is that at its peak, its velocity is 0 because it's not traveling upward or downward at that instant. So when I want to figure out how high it went, the first thing I should do is figure out at what time it's at its peak. And I can do that using my velocity function because I have a velocity function now that I can use, and I can just say, when is my velocity 0? So when is negative 32t plus 128 0? And I just need to solve this now. So negative 32t equals negative 128. So t equals 4. So now I know that at time 4, it's another thing that I've detailed here, at 4, the velocity is 0. and that's going to be the peak of the arrow. So we can keep moving here. We still don't know how high it goes, so what I want to know now is what is the position when the time is 4? And so now I need a position function. So that's negative 16t squared. I'm taking the antiderivative of velocity and leaving room for some possible constant there. Okay, so now I have a position function, and I want to know how high it goes. So what I need to figure out is what is that constant value, because I can't solve this equation until I have that constant value. There is another initial condition. We know that when we're laying down at the beginning, or when the person who's shooting the arrow is laying down, they're laying down on the ground when this arrow is shot. So when the arrow is shot, our position is 0. So that tells us that, and I'm going to put that over here, that S of 0, which would be negative 16t, or 0, sorry, squared plus 128 times 0 plus c is 0. So there is no constant. All right, so now that we know that, we have a specific equation for position. And so to answer these questions, we can use these functions that we've created. We've got our position function, we've got our velocity function, we've got our acceleration function. So how high does it go? Well, what I can do is just figure out what the position of my arrow is when time is 4, because we figured out that at 4, the velocity is 0, which must be the peak of the arrow. So I can just do S of 4 equals negative 16 times 4 squared plus 128 times 4, and this is my work for A here, and so that ends up being 256 feet. So the arrow goes 256 feet in the air. Question B says, how long does it remain in the air? So now what I'm thinking about is, as this arrow is shot up, it starts at a position of 0, it goes up to 256 feet, which we just figured out, then it turns around and it comes back down, and its position will be 0 again. So again, what I want to know is, when is my position function 0? We know that one of those times is when t is 0, but we don't know the other one of those times. So we'll use our equation, which is negative 16t squared plus 128t, and find both zeros. I know one of them is 0. So we're expecting one of these roots of this quadratic to be 0. If I factor out a GCF, it would be a negative 16t. All right, and that's going to leave us behind a t minus 8. And so now we can figure out our roots. If I set negative 16t equal to 0, I get t equals 0. And if I set t minus 8 equals 0, I get t equals 8. So we knew about that one because that was our initial condition. This is the one we're using now. So now we can say the arrow remains in the air for 8 seconds. All right, so I think I'll post the work for the second two, and if you'd like me to go over it in a video, then contact me and we can set up some time today and do an extra help session. All right, but since this is the most recent concept, maybe this isn't the thing you need the most practice with.